Which tryptophan residue of carbonic anhydrase can be selectively modified at CHCl3 with CHCl3 at 20 degrees Celsius? All right, let's take a look. CHCl3 means we're looking at the first two rows here, and we have two different buffers, A and B. If we look at buffer A, it looks like with CHCl3, you're going to be modifying tryptophan 4, 190, and 243, so it doesn't really matter. But with buffer B, it looks like nothing's going to be changed except for tryptophan 243 at 55%, meaning you can selectively modify tryptophan 243 if you use buffer B with this reactant CHCl3. So you can selectively modify tryptophan 243 based on the table. I realized I should go over A, B, and C. So tryptophan 4, it's just CHCl3 like I said, tryptophan 4, 190, and 243 with buffer A. You can selectively modify 4 since if you want to modify 4, you'll have to modify 190 and 243 as well. If you want to modify 96, well, you can't do that with CHCl3 at all since there's no modification across these two conditions. And for tryptophan 190, like I said, if you want to modify this one, you'll have to use buffer A since buffer B, you don't get any modification. But if you use buffer A, yes, you modify 190, but you also modify 4 and 243. So you can't selectively only modify 190. All right, let's move on to the next question. This is, which classification of amino acids applies to the tryptophan residues after photochemical modification by CCl3CO2H? All right, so what happens when we modify with CCl3CO2H? Let's take a look. So we have it right here. We have this reactant CCl3CO2H. And what do we get? We get the addition of a carboxylic acid group, right? Well, like the name implies, this is an acid. So it's pretty straightforward. If you know what this group is, you'll know that this is a carboxylic acid, meaning this new amino acid is going to be acidic, making A. It's not basic. It's not a base that you're adding, not hydrophobic, especially since the carboxylic group has hydrogen bonding potential, and it's not polar neutral because, like I said, it does have hydrogen bonding potential, making it A, acidic. All right, let's move on to the next question. This says, which type of heterocycle is found on two amino acid residues blocking access to tryptophan 15? So if you'll recall, we'll go back to the passage. It does tell us which of the amino acids block tryptophan 15. It's blocked by the two histidine residues and one lysine residue. All right, well, we know it's asking about the two amino acid residues portion, so that's the two histidine residues we're talking about. So it's asking, what is a heterocycle found on histidine? So this is the structure of histidine. And essentially, it's asking, what is this? What is a heterocycle? Oops, that is not a very good circle. All right, a heterocycle is a cyclic molecule that contains an element that is other than just carbon and hydrogens. That's the reason it's called hetero. You have other things that are not just carbon and hydrogens. So in this case, you have nitrogens as well. So what is this group called? This is a pure discrete, basically. Once you know once you read the passage, you know it's histidine. There's no other way to solve this other than just knowing it's histidine. Or other than knowing that this heterocycle is called imidazole. I don't actually know how to pronounce that, but that's the answer, imidazole. Let's go over indoles and the other groups here. Indoles. So indoles are actually what you find on tryptophan. So this is the group right here. This heterocycle is an indole. So you do need to know these different groups and the names of these groups. Wow. There we go. Not there we go. Huh. Interesting. All right, well, you do need to know the names of these groups as they are going to be tested on the MCAT. They're very common. So names like imidazole, indoles, pyrimidines, which you should know are classes of bases for like nitrogenous bases, the DNA nucleotides. There we go. Sorry, the basis for the nucleotides. And pyrrole, this is this group right here. Also another heterocycle, just not the one we're looking for. You should know the names and the structures of these. They're definitely fair game for the MCAT. Even if other people don't think so, I can assure you that this is fair game. I don't know why it's. There we go. Let me see if that works for this. Okay. I actually lied. There is another way to solve this problem through the passage if you're a little clever. But the easiest way and the most surefire way that you'll get questions like these right is to just memorize the structures of these molecules or these compounds that are listed in the answer choices. So let's take a look at the passage. So in the passage it says that the aromatic side chains are going to be chemically modified. And it tells us that the substitution on tryptophan, blah, 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 is somewhere on the indole ring. So what that clues us is that the structure we're looking at right here, that they've drawn in figure 1, this structure, this is an indole. Well, if you know this is an indole, and you know this is a tryptophan, and you know you can piece together that tryptophans have indoles. So what that means is if you know it's not going to be a pyrrole, if you know it's not going to be a pyrimidine, and you know that indoles belong on tryptophans, then you know that the only group that histidines can have that you haven't thought about yet is going to be the imatazole. So that's kind of a way you can think about it. But like I said, again, the best way is just knowing the structures of these compounds that are listed out here. All right, let's move on to the next question. It says, based on the passage, what most likely causes tryptophan 96 to be accessible to CHCl3 at 75 degrees Celsius? So let's take a look at the passage again. Remember, tryptophan 96, they're modified by this at 75 degrees, which what? Fully denatures this protein, okay? But leaves the primary structure intact. So what does that mean? What does denature mean? Denature means if you have a folded protein like this, it's going to unfold it like that. All right, it just basically means instead of a folded protein, you have an unfolded protein, but that doesn't mean anything breaks, okay? So let's look at A. Peptide bonds are broken, releasing this amino acid. Like I just said, denature does not mean you're breaking it, breaking the protein. Not only that, it tells us that the primary structure is intact. What's the primary structure? That's going to be the amino acid sequence. So if that's going to be intact, that means the peptide bonds cannot be broken. There we go. Reduction of disulfide bonds occur. You only reduce disulfide bonds when you add a reducing agent, but here we're only raising the temperature. That tells us the protein is only denaturing, and it's not that the disulfide bonds are breaking. Again, disulfide bonds only break if you add a reduction agent, or reducing agent, sorry, but we haven't added that here, so that tells us that it can't be B. The protein unfolds and exposes W96 or tryptophan 96 to the buffer. Now that's more likely. Like I said, denaturing means the protein is unfolding, and as it unfolds, all these amino acids that would normally be in the middle here that are shielded from the solvent, now they're just on the surface, right? All of the amino acids are accessible by the buffer. So C is much more likely. And finally, D, CHCl3 extracts W96 or tryptophan 96 from the protein interior. Extracts. What does extract mean? That means you're taking this single amino acid out and you're somehow exposing just that, or you're pulling that one out just to expose to the buffer. Well, that's very unlikely. I don't even know how that would happen, chemically speaking. I don't know if that's even a technique. But regardless, it's just an unlikely event. It's a very difficult event, I would assume, if it's possible at all. And like I said, denaturing, you're unfolding the entire protein. You're not just unfolding a small segment just to release one amino acid, or just to expose one amino acid, meaning D is incorrect. All right. What is the name of the ionic compound used to make buffer B? So let's take a look at what buffer B is. We see buffer B written out here for us. NH4 CH3CO2. NH4, that's ammonium. Unfortunately, that doesn't help us here. So we're going to have to rely on the fact that we're given CH3CO2. So we're looking for something that matches CH3CO2. Now, unfortunately, from here, there really is not much else you can do other than just know what these different compound formulas are, or the structures are, which you can figure out the formula from. So we'll just go through that. So ammonium formate. What is formate? Formate is this right here. All right, so what would the structure of this, or the formula for this be? HCO2 minus, right? A cannot be correct. Carbonate, what is carbonate? That is when you have right? So that's CO3 2 minus, actually. Again, not the correct formula we're looking for. Bicarbonate's almost exactly the same, except instead of a negative sign here, you replace that with a hydrogen. So the formula for bicarbonate would be this. Not the correct formula again, leaving us with acetate. So what is acetate? Again, these eights, the ATE, I should probably mention this. ATE signifies that it's going to be the deprotonated form of some kind of carboxylic acid. So like carboxylate, that's the formula for naming carboxylic acids that have been deprotonated. So acetate. Acetate is the answer we are looking for, which is this right here. So it's the most common, or most, I guess, one of the most common forms of carboxylic acid, I would assume. What's the formula for this? We have the methyl group in the beginning, CH3. Then we have the carbon in the middle, 2 oxygens, and a negative sign. This is the formula we're looking for, CH3CO2, meaning D has to be the correct answer. So not much else you can do here other than know the structures or the formulas for these compounds. One thing you guys should keep in mind is that ATE, that suffix at the end, does mean it's going to be the deprotonated form of a carboxylic acid, as in a carboxylate.
Which chromatographic, which, I need to talk slow when it is. Okay, let's go. Which chromatographic technique would most likely separate a mixture of native carbonic anhydrase from carbonic anhydrase photochemically modified by CCl3CO2H? All right, so let's see. What does this compound do? We see right here, oh, this makes an acid, right? We have this carboxylic group, or carboxyl group. Okay, so what does this carboxyl do for us? It's going to, what is this? It's an acid. So what does that mean? It's going to be deprotonated, lose that hydrogen. And what does that mean? It's going to have a negative charge, okay? So the one that's modified by this compound, that's going to have more negative charges compared to the native. Well, if you want to compare or if you want to separate out compounds that have negative charges versus those that don't have as many negative charges, what do you want to use? You want to use anion exchange chromatography. Remember, this is when you want to separate out a compound that you want has, or you're separating out molecules based on their negative charge. Okay, so the compound that you would like to separate out is going to have more negative charges than the one that don't, or the ones that, or the other molecules that you don't want. So like I said again, the modified version of carbonic anhydrase has more negative charges due to this modification, which means you want to use anion exchange chromatography to take this out. You want to use cation exchange since we're looking at negative charges, not positive charges on these molecules. Gas liquid chromatography, unfortunately, this is dependent on vapor or basically boiling points. The issue here is before you reach the vapor point, you're just going to completely denature the proteins that you're interested in. So that's not a really good idea here. And finally, size exclusion chromatography. Now, some of you guys might think if we add this molecule here, the modified version of carbonic anhydrase is going to be bigger than the native carbonic anhydrase, meaning that you can use the size exclusion chromatography. Unfortunately, although that line of reasoning is correct, size exclusion chromatography's resolution is not that high. In other words, it's not going to be able to tell the difference between one that has this carboxyl group versus one that doesn't. According to AAMC and for the purposes of MCAT, if the difference is less than 1 kilodalton, okay, or there we go, kilodalton, it's not going to be a big enough difference for the size exclusion chromatography to basically resolve out those two different molecules. So it's not going to be D either, meaning A is the best answer here.